Welcome to the series of regression analysis. So we are starting with a very basic understanding of the regression analysis. You know that regression line is the model line that is actually representing to the all data points. So these are the actual observation that you can see, the dots that I mentioned here, and there could be multiple regression lines. For example, in this case, you can see that we are having a one regression line. And the important thing is that we need a line that is giving a perfect fit, or in other words, it should be representing to the old original data observation. So let's dive in to understand the basic idea of the regression analysis. As we have discussed that before we establish a relationship between two variables, we need to understand that there should be some logical connection. There should be some perspective uh, that explain the relationship between two variables. So here in this case, we are taking two variables. The first one is the weight and second is the height. So we are going to establish the causality between the weight and the height. And here we are having three observation. And imagine we have a data set that records the weights and corresponding height of different individuals. Given someone weights, can we predict their most likely height? So in this case, we want to predict the height per unit change in the weight uh, in units of kg. So this is the classical regression problem, predicting a continuous output like height from an input feature like weight. So once we plot the weights and heights on the regression plane, here we can see each dot representing to the each original observation. And once we plot the weights and heights, we can see all the dots here, and we need a regression line that actually representing to the all data points. So here we are having a model line or a regression line where we are having two important uh, parameters which were earlier unknown. Now this regression output will be giving us the answers of two unknown parameters. So first one is called the y-intercept, which is the point where the regression line is cutting to the y-axis. And the second parameter is the slope, which is the rate of change on this particular regression line. And so we can say that simple linear regression works by drawing a single straight line through the data that best captures this trend, and we call this is the best fit. Again, earlier I have mentioned that there could be multiple regression line that could be passing through these points, but we need a line that is actually having a best fit. And what does it mean by the best fit? So we'll discuss in a moment. So best fit line is in fact a line where the actual observation and the regression line uh, having the least distance. So we can say that we have to calculate the error, the difference between the actual observation and the regression line. So the best fit line is the one that is closest to the all data points collectively. We measure these closeness by vertical distance between each actual data point and the point predicted by our line. This distance is called the residual error. And our goal is the one line where the sum of all these errors is as small as possible. And here you can see uh, the regression equation, which is y is equal to mx plus c. There are various forms through which we can actually express the mathematically the regression line. It could be y is equal to a plus bx, or it could be y is equal to alpha plus beta x, and so on. And here, if we draw this equation in this form, where we can clearly see that there are two important parameters, which is theta 0 and theta 1. So these are the unknown parameters. And in regression analysis, we are interested to calculate these two unknown parameters. So theta 0 is the y-intercept, the point where a regression line is cutting to the y-axis. So this point actually lies here. And the second parameter is the theta 1, which is the slope, which is the rate of change on that particular line. And now the question is that which theta 0 and theta 1 we are interested to calculate. As we know that there could be multiple regression lines that could be drawn, and but we need a regression line which is actually best predicting uh, to the behavior of the data. So we are interested to calculate the theta 0 and theta 1. And let's assume that if we are having this regression line, so this is the one of the case where you can see, and this is the origin where x and y values are starting. So it is the point where the y-intercept is 0, and assume that there, in this case, the slope is zero point 0.5. So my question is that is this regression line shows a best fit, because there could be a possible model as well where there could be a y-intercept, but there is no slope, and so if there is no slope, it means that there will be a horizontal line. So there could be multiple scenarios. There could be multiple regression lines, but the question is that we need a theta 0 and theta 1 value that actually best represent to the model values. So if we start guessing the theta 0 and theta 1 values randomly, so we cannot reach to a perfect solution, because the ideal values of theta 0 and theta 1 would be where the error will be minimum, each observation distance from the regression line. So if we start doing this, you know that it will take so much time, and we cannot reach to a optimal theta 0 and theta value, which actually represent to the best line. So solution of this problem is to find out the cost function. Uh, the cost function means that a better line that is actually representing to the all points. If we see the mathematical computation, the cost function would be seems like this way. This is the error term, in fact, and you can see that. And we want a cost function where theta 0 and theta 1 values shows the optimal result for the model values. So this is the model result, and this is the actual observation. So what we are trying to do here is that, and we know that the difference between the predicted and actual value is called the error term. So what we do is, in order to uh, cancel out the negative values, we'll just take the square, and this is also called the sum of square of error. So by taking the square, this makes all error positive and penalize large errors more heavily. And eventually we reach to the cost function, and 1 over 2 is included for mathematical convenience. So we can say that we need a cost function or sum of square of error where uh, we can actually find out the optimal value of theta 0 and theta 1. Or we can say that we need theta 0 and theta 1 where the cost function or the error term will be minimum. So this is something the important take that you keep in your mind. And if you look at this scenario, there could be, again, as we have discussed, there could be multiple scenarios where there could be multiple beta coefficient values in the regression line. But we want theta 0 and theta 1 where we will be having a minimum cost function. So here in this graph, you can see that if we keep increasing the theta 1 value, we we are actually dropping the cost function. So this is the minimal point where theta 1 value reflecting the least cost function. So in this scenario, you can understand that there could be multiple theta 1 values, But we need theta 1 and theta 0 where we will be having a minimum cost function. And this idea is something important for you to keep in your mind. So in every regression analysis, we try to find out the cost function, which is minimum for theta 0 and theta 1. And again, because we are using the software, and these theta 1, theta 0 values automatically calculated by a software. So, but you should know that the basic understanding of the regression analysis. Hopefully, you will get the basic idea about the regression analysis. Thank you.